Morning, everyone. So yesterday we had a look at acid-base indicators. Pretty much they were chemicals where in the acid form they were one color, in the base form they were another color. Most of our indicators are weak organic acids and bases. We need them to be weak so that they actually have an equilibrium and they can actually shift left and shift right. Remember, every chemical indicator is its own chemical structure. It has its own special Ka value, and what that corresponded with is it had a very special pH at which they actually change color. So just let me start you off with a quick warm-up here. We're going to be utilizing these indicators to have another look at our titrations. For this one, I want you to find for me what color is, here's an indicator, chlorophenol red in a 0.050 molar HCl solution. And I want you to calculate the Ka value. Okay. So the experiment is very simple. We have a beaker, right? Currently sitting in the beaker is 0.050 molar HCl. We practice a lot of this here. Given a chemical, ask yourself, what is this chemical? Is this one here an acid or a base? Is it a salt? Well, this one here is an acid. Is it strong or weak? Well, this one here is a strong acid. So being a strong acid, we know at one-way arrows, it ends up forming H plus and Cl minus. If you know the concentration is 0.050, I know that the H plus is 0.050, the Cl is also 0.050. Even though I typically just sort of leave my work like that, it is understood that the HCl is completely ionized. Cl minus actually has no ability to hold hands again with the H plus. But what we're concerned with here is, oh, the H plus is actually 0.050. Because when you check your table, you can find chlorophenol red on your indicator chart. For chlorophenol red, we're given the pH range at which it changes is 5.2 to 6.8. And then on the side, it actually gives you the actual color change. Somewhere within that pH range, it changes from yellow to a red color. We need to know what is the pH of a current solution, because then I can sort of match it up against what the pH range is. So let's find the pH. It was really easy to find the H plus for something that was strong. So we're just going to take what is the negative log of 0.050. Negative log 0.05 gives me here a pH of 1.30. A reminder again, for pH, the significant digits are after the decimal place. So we're heavily in the acidic region. You can think about the indicator equilibrium. H in is donating a proton, becoming N minus. In a heavily acidic solution, you have a ton of H plus. That's going to shift the equilibrium over. We're going to have way more of the acid form than the base form. Okay? Because we're going to be in the acid form, we're going to be the acid color. In this case here, it's going to be yellow. If I just plotted this on a sort of pH ruler here, so we are currently at a pH of 1.3 way over here. It took somewhere between 5.2 and 6.8. That's when the indicator actually changes color. Just for simplicity, we had defined what's called the transition point as the midway mark. Take an average between those numbers, 5.2 plus 6.8 divided by 2. Well, the midpoint here is actually 6.0. That's when we cross over. It's yellow, 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 yellow. Once you pass 6, then it switches over to red. So we've answered the question. If I drop a few drops of this chlorophenol red, the chlorophenol red is actually going to show a yellow color because it is currently in the acid form. Right? Then they suddenly ask you, what is the Ka of this indicator? Again, if you know the relationship, it's really easy. If you don't, it's impossible. Remember what we did last day is we actually said at the very special pH of 6 for this indicator, the acid form and the base form actually equal out. They actually canceled out, actually giving you a relationship. The pKa of your indicator is actually the pH at the transition point. And remember, every indicator has its own transition point. This time, my transition point here occurred, my halfway mark is 6. So pKa here is actually equal to 6 for this indicator. I can pretty easily find the Ka. It's going to be anti-log of negative 6. So that's just going to be 1.0 times 10 to the negative 6. Okay? And there you go. We found the Ka. I have still no clue what the chemical structure is. I have no clue why it has these colors. But I have a way to actually calculate what this Ka value is. Today what we're going to do is we're going to join some of this indicator discussion back to our titrations. The whole frustration with titration up to this point has been, let's imagine we're using phenethylene. It's colorless, colorless, colorless. Oh no, it's overly pink. And now you overshot it. Now you need to redo it. I'm going to show you a slight little spin off of the question here to see how we can actually deal with that without having to start over. Okay? So just a different look at a titration here. And we're going to look at it in terms of something called a titration curve. Some of these calculations get to be a little bit scary later on, but it's just some of the main ideas I want to just introduce to you. So we are still doing a titration. We are still trying to find an unknown concentration. What we're going to be doing, though, is we're actually going to be using a pH meter as we do it. Okay, so titration curve, we're going to have our burette. Again, it doesn't have to be based in the burette, but usually most of our titrations have been. So let's do NaOH. We're going to drop it into some unknown amount of acid. So we had maybe HCl in here. What's unknown is not the chemical. I know it's HCl. The unknown part here is the molarity. This one here could be really concentrated. It could have a lot of H pluses. It could be already diluted down with a lot of water. What I'm essentially doing is I'm using the base, dropping in the base slow enough so that I can actually count how many H pluses are present. If I try to do this balanced equation here, this is the first titration curve we're going to do. HCl and NaOH, this is a titration between a strong acid and a strong base curve. At the equivalence point, basically I would have just dropped in enough base. That base here can no longer find any more H+. That special point when I want to stop, called the equivalence point, is when I've neutralized all the acid and all the base is gone, and now we've gotten to NaCl and we've gotten to water. So I just want to rehash that really important term for you here. That's called the equivalence point. We want to add the base until we hit this point. Equivalence point is sometimes also called the stoichiometric point. Basically, there is a mole ratio between the acid base that it should be. I don't know how much H+ there is. I'm just dropping a base and slowly trying to count how much H+ there is. At the equivalence point here, the moles of H+ equals the moles of OH-. Another way of saying that here is we've just hit, well, since the mole ratio is 1 to 1, you've just added in the same moles of base to neutralize. Okay, so that's the equivalence point. That's when we know to stop. The only problem with this titration, unfortunately, is all these ones here are soluble salts. They're also colorless. I know I want to use the NaOH. I know I want to add it slow enough to stop immediately when the H+ is canceled out, but I don't know when this happens because everything is colorless. If I accidentally dropped in a whole bunch of hydroxide, I wouldn't have any clue because this one here would still stay colorless. So what we actually did for these titrations was we actually added in a chemical indicator. The indicator that we chose was phenolphthalein. Now you see on your table there's actually a few other indicators depending on what your pH is expected to be. Phenolphthalein, we learned from yesterday's lesson, between 8.2 and 10, it changes from colorless, being an acid, and it changes to a pink color. So what we did is we chose an indicator. We're hoping that the indicator is going to change color. Notice that the phenolphthalein actually changes color a little bit late. The halfway point between 8.2 and 10 is actually 9.1. When the indicator changes color, it senses that there's an excess of hydroxide, and that's when I know to stop. You can be really silly and you can choose an indicator. Maybe the indicator changes color at pH 2. Sure, you can get the color change to happen, but the color change doesn't tell me anything about the equivalence. It's no use to you. Okay, so remember the frustration was we added phenolphthalein. I know as I get close to this equivalence point here, the pink color stays longer and longer. I want to look for that pale pink color, which is sort of the transition point color, the blend between colorless and pink. If I accidentally open the burette valve here too much, I now have an excess of hydroxide. Now I don't have a good count of how much acid particle there is. I want to stop at the equivalence point here so that I can do some stoichiometry. What we're going to do here, another look at this titration. Instead of using an indicator, we're going to instead stick in a pH probe. Okay. Now we don't need to worry about how a pH probe works, but as the name suggests, it just samples the pH as you drop in the NaOH. So this is how we're going to do our titration curve. We're going to slowly drop in our NaOH. I'm going to plot the pH that my meter is reading at all times, and I'm going to plot it against this time I'm adding NaOH, so volume of base or volume of NaOH added. And what it's going to do is it's going to just record what is the pH of the solution. So for starters, we had an HCl solution. We were really, really acidic. We'll assume we're at 25 degrees, so 7 is neutral. Being really acidic, we know that we're really far away from 7, a really small number. Because this one here is a strong acid, again, based on the molarity, it may be actually a little bit higher as well. But being a strong acid, I would expect the pH to start off very low. This is when I had added in no base yet. This is before I started. Then what I'm going to do here is I'm just going to add in just sort of increments of NaOH. Let's add in sort of 1 milliliter increments just for kicks. As I add in that 1 ml of NaOH, what's going to happen to this pH? Well, at first the H plus was sort of all there, the pH was really, really low. As you steadily drop in hydroxide, the hydroxide kills the H plus. We're going to slowly get less acidic, so the pH should actually start climbing. I drop in another mil, it should climb. I drop in another mil, it should climb. And depending on the relative concentrations, this one might climb really quickly or climb really slowly, but nonetheless here, this one should climb. Strangely, there is going to be a certain point as I'm doing this test. Strangely, there's going to be a point, okay, so the pH is increasing, it's getting higher and higher and higher, and then suddenly, at some special pH, it suddenly shoots up really, really quickly, and then it starts leveling off. Okay. Part of the reason for this shooting up part is because the scale, remember, pH is actually logarithmic. So remember, it's based on powers of 10. It's not actually linear. So going from 7 to 6, right, that's only 10 times more acidic. Going from 7 to 5, it's actually 100 times more acidic here. As I get to these really low acidities here, even really huge change in H+, it's not actually going to change much in terms of the y-axis. As I get close to neutral, that explains partially why this one here can jump so suddenly. It doesn't explain all of it, though, because all I'm doing is I'm adding in base. How come, well, the pH was changing so gradually, how come there's a point that it changes so suddenly? What I want to analyze with you here is, as I get closer and closer to the equivalence point, as the amount of base I'm adding actually matches up to the acid, I'm going to have a situation where I have one very last particle of H+, right? Again, I have no clue how much H+ there was. I'm just dropping in base to try to count the H+. But I'm going to have a situation where I have that one very last particle H+. H+ here is still acidic. It's still going to give me a acidic pH. You're going to drop in maybe a half drop of NaOH. That OH minus here would have killed off the H+. Now all the base in the acid has neutralized. That should give me a neutral pH. That explains the sudden jump there. And then you drop in another drop of hydroxide, and now the hydroxide can't find any more acid particles. The hydroxide is basic. Within a matter of 2 drops, we've gone from having that very last acid particle to completely neutral to completely having base particle. That's the point I actually wanted to stop, right? So usually when you do this titration plot here, you essentially just track down the pH as you steadily drop in the NaOH. You're looking for this jumping up region. The middle point of this jumping up region is called the equivalence point. For a strong acid, strong base curve, the equivalence point, that's the point when the H+ has just killed off the OH minus. For a strong acid, strong base curve, the pH is equal to 7. Which shouldn't really surprise you here. At the equivalence point here, I've just added enough base to kill off all the acid. Since there's no acid or no base left over, the pH should be 7. As you then switch over to other curves later on, we are going to find, yeah, equivalence point here does mean the reactants are all gone, but sometimes it's the salt that actually screws things up. The salt may actually generate some acid. The pH may be lower than 7 or above 7. More on that very shortly. So we're going to find that the equivalence point here, I can write this down here. Why does it shoot up so quickly? Within a small addition of NaOH, in this case here, it looks like it's happening somewhere about 4, because it is graphically, you can actually line it up even better. Within a small addition of NaOH, we go from one last H+, so it's acidic, so that's this point here. One last H+, to neutral, so that's going to be this point here, to OH minus, close to the equivalence point. Okay, and that's why this one here shoots up. That's when we're going to stop. This point here is going to be very important for us here. We're going to call it VB, and that's going to be the volume that you needed to reach equivalence. If this thing here were really concentrated, you would need to drop in a whole lot more base. Maybe the curve here would push over a little bit, and then it's going to shoot up. Basically, you look for when this suddenly jumps upwards, because when that suddenly jumps upwards, we know we're close to the equivalence point. Now, how come we were able to do this titration without pH meters and all that? Remember, what we did experimentally was we actually used an indicator. The indicator actually changes color. The indicator was phenolphthalein. It changed color 8.2 to 10.0. Wait a second. 8.2 is about here. 10 is about here. The indicator phenolphthalein actually changes color a little bit too late, right? At a pH of 7, when we expect the equivalence point here, the phenolphthalein is still colorless, right? It's colorless only until the sort of midway region at 9.1. Only then it changes to pink. So this is actually a systematic problem. We actually realize, the phenolphthalein actually changes color a little bit too late. But the reason why it's actually a good approximation, because within a very, very narrow region of base, you don't have to drop in too much. Within a very, like maybe a half drop or something, we basically blow through, cancel out the H+, we neutralize it, we now have excess base. If you would have blown through the pH 7 point that we're looking for, we probably blew through 9.1 as well. So pretty much when that color change occurs, yes, technically it's too late, but because this all occurs within a very narrow range here, if you read the volume that you dropped in from the barrette here, by the time the color has changed here, that's pretty close to the volume of the equivalence point here. So let me just write this down in words for you here. Phenolphthalein, this is the indicator that we very often use. Phenolphthalein actually changes to pink too late, right? Because we're looking for the pH 7. That's when I should have stopped. Phenolphthalein only changes color roughly around 9.1, but it is a good approximation. Based on my earlier point, good approximation since it all happens at VB. It all happens within a very narrow range. You just dropped in that half drop of base. As you kind of went past a pH of 7, completely neutral, you probably would have gone past 9.1 as well. Okay? So even though technically it's a little bit too late, phenolphthalein is a good indicator. Phenolphthalein, its transition point is 9.1. We want to choose, let me write this down as well, also important, okay? We want to choose an indicator with a transition point or endpoint. That word transition point or endpoint refers to the indicator. That's when the color change happens. Choose an indicator with transition point or endpoint close to the equivalence point or the stoichiometric point. I want it in such a way that by the time the indicator actually changes color, that actually tells me to stop. Because this is a hypothetical here. I saw a whole bunch of other indicators in my earlier lesson here. What if we chose an indicator that changes color like thymo blue? It changed color at pH of 2. So thymo blue changes from red to yellow at a pH of 2. Would the color change still occur? Sure. You drop in a few drops of thymo blue here. Maybe it starts off red. Oh, look, the red changed to yellow. But notice, this color change point has nothing to do with the equivalence point that we're actually interested in. So that would actually be a mismatch. That wouldn't be a good choice. Even though phenolphthalein changes color a little bit too late, it does happen somewhere around the equivalence point. At the end of the day, I want to do stoichiometry. I want to make sure that there's no excess. I want the indicator, when it changes color, to tell me to stop, because that actually indicates something about the equivalence point here. Okay, so there we go. That's how we do a titration curve here. In fact, with the indicator inside, this is going to go to a really deep pink color. I'm going to say keep adding, keep adding, keep adding. Get a few more little data points here so that you can actually figure out where this shooting up region is. Okay, where it shoots up is going to be the equivalence point. We basically use this volume, and there, that's the titration point when all the base has killed off the acid. It's a little bit more interesting when we actually do a weak acid strong base curve. So let me just jump into this here. Also a titration curve. Let's just do a weak acid against a strong base curve. Okay. So as an example of this here, a weak acid could be Chaku. So acetic acid, we're going to react with NaOH. We can balance the equation, no problem. It's going to be in a 1-to-1 ratio. The acetic acid is going to lose its H+. That's going to neutralize the OH-. We're going to get sodium acetate, NaCH3COO, and we're going to end up getting water. Experimentally again, this is going to be, we have the solution in the barrette. Just for familiarity's sake here, I'm going to drop in base. You could very well drop in acetic acid. It's exactly the same. We have some unknown concentration, some question mark molarity of Chaku. This one here is a weak acid, like we've been saying. This weak acid doesn't ionize very well. It doesn't break off to form a lot of H+. So being a weak acid here, I only expect a few odd H+. The whole point of doing this titration, again, I'm going to drop in the OH-. As long as OH- finds an H+, it neutralizes, not done yet. I'm looking for the equivalence point when the OH- has killed off all the H+. Now the question here is, I just emphasized this is a weak acid. Do you think it's going to take more volume, the same volume, or higher volume of base to actually neutralize this H+? At first, you may be thinking, well, if this is a weak acid, we've done a bunch of Ka calculations, right? The Ka constants are really tiny. you only have so little H plus, it's not going to take that much base to actually kill off the H plus. That would be true. You're right. There isn't a lot of H plus because of the acetic acid, but notice, because the weak acid is constantly in equilibrium, as the hydroxide is added, as it kills off the small amount of H plus, it pulls down the H plus. How does the equilibrium respond? The equilibrium is going to respond by trying to produce some more H plus to try to regenerate some more H plus until when? Until you've actually added in enough hydroxide. You keep pulling down this small amount of H plus, small amount, until you completely use up the weak acid. So let me just write this down in words here. Although the weak acid ionizes slightly, as the H plus is neutralized, the equilibrium actually shifts right. It actually replenishes, shifts right until the acetic acid is gone. So back to my earlier question here, would it take more base, less base if this were compared to a strong acid? It's actually the same volume. Same volume needed to reach equivalence compared to an equimolar. Equimolar just means the same molarity. Equimolar strong acid solution. So the implication there, earlier we were doing, well, HCl against NaOH. Well, HCl is a strong acid. It one-way arrows, forms H plus and Cl minus. It just delivers the maximum H plus all at once. There's no shifting equilibrium that's needed. The OH minus is just used to kill off the H plus. Acetic acid as its equilibrium is really poor at forming H plus. So CH3COO, it's an equilibrium. It's really bad at actually protonating. It's actually really bad at getting rid of this H plus. We started off with a ton of acetic acid. It's heavily reactants favored. We only have a little bit of H plus, a little bit of Cl minus. But due to this shifting and due to the equilibrium, as the OH minus kills off a little bit of H plus, shifts more. Kills a little bit more, shifts more. Kills a little bit more. You will eventually kill off the same amount of acetic acid. If these were equimolar, let's say I had 1 molar solutions of both of them would require the same volume to reach equivalence. If we had a titration curve here, if we had 4 point something was the equivalence point for the strong acid, if the acetic acid was exactly the same, it would also take about 4 point something to actually reach equivalence, even though it didn't all ionize all at once. So let me just sketch for you what this curve would look like. So we're going to have tracking the pH as I steadily drop in volume of our NaOH added, our base added. Now, some key points to keep in mind. Because acetic acid here is a weak acid, obviously, if the concentration were really high, we can still get into the really, really low pHs. But because this one here is a weak acid, we would expect the pH to not be as low to start. Okay, so probably the pH starts a little bit higher, right? Not as acidic as before. The strong acid would have been down in the, usually we quote like 0 to 2 kind of range. Weak acids are typically between 3 to 5. Obviously, that would differ depending on the concentration. But we start out a little bit higher, and all you're going to do, I haven't added any base. I'm going to add in base here at equal increments, and I'm just going to be tracking the pH at the given time. I'm looking for the shooting up region to tell me when the equivalence point is reached. So this curve here, steadily I'm adding base. I'm killing off the little bit of acid that's in solution. A little bit more is shifting over, but overall it doesn't completely replenish the H+, so overall it is going to be basic. We're actually going to get a slightly interesting shape here. So as I add in maybe 1 mil, it's going to go up, 2 mils, it's going to go up, 3 mils, it's going to go up. As I steadily do this here, we're going to get a sort of like curvy shape like this. Right? It is increasing, it is changing, but it's not increasing very quickly. Again, because of all the shifting, if we start with equimolar, if the strong acid was the equivalence point here around the volume of 4 region here, this one here will also shoot out at about a pH of 4, a volume of 4. So this one here is going to shoot upwards, and it's going to end up going higher. If you use phenolphthalein, it would turn pink. Take a few more readings here. I want to make sure I can see this shooting up region very well. So first thing that we just said here is the VB, right? This is the volume of base here. It was somewhere close to 4, maybe a little bit over 4 here. The VB, this is the volume needed to reach equivalence to reach this sort of jumping up point. This jumping up point, the midway point is actually the equivalence point. Curiously, the equivalence point here for a weak acid strong base curve, the equivalence point actually has a pH that's bigger than 7. We're going to come back to that in a second. So we have that shooting up point here. There's also one special region here. There's a region where I'm actually adding quite a lot of base, or you can add quite a lot of acid to go in reverse here. But the pH really isn't changing all that suddenly. It's only once this part here runs out, then that's when the pH jumps suddenly. In that case there, we're going to refer to this as a buffer region. We'll come back in a few classes time here to figure out what is a buffer and how come that was created. But those are some key aspects of a strong base weak acid curve. So let's come back to this first observation. How come the equivalence point is actually bigger than 7 at equivalence point? Let's just have another look at our equation. I'm just going to sketch it down for you here. We have acetic acid. It's going to react with NaOH. For neutralization, this is always going to be a one-way arrow, even though acetic acid internally has an equilibrium. Basically, the base is killing off the acid particle here. This is going to end up forming sodium acetate, like I wrote earlier, and forming water. I want to write this down very clearly for you here. At the equivalence point, remember we've been saying the moles of acid equals the moles of base. That's the point I want to stop. I wanted to use the base to actually count how many acid particles were actually in solution. So let's just do that here. At the equivalence point here, I had some unknown amount of acid. If the acid was really, really concentrated, I would go through loads and loads of volume of the spiret before this equivalence point is reached. If it was really, really dilute, I wouldn't need that much volume. Depending on how much I'm actually dropping in before the shooting up point happens, I'll know when to stop. Okay, so in this case here, at equivalence point here, I had a bunch of unknown acid. At the equivalence, I've just added in perfect amounts here. The base has perfectly killed off the acid. I have no more reactants. I also have no excess because I don't want to have the phenolphthalein turn to a pink color. I don't want an extra where I can't do any more stoichiometry. Since I have no acid, no base, I would expect the pH to actually be 7, right? However, in this case here, although at equivalence point here, moles of acid equals moles of base, no reactants should mean completely neutral, should mean pH 7. But here's the kicker. But the salt that we create, the sodium acetate that we form, but the salt actually hydrolyzes. That's why we did hydrolysis in the first section. The salt actually breaks up, it reacts with water to recreate some OH minus. I'll show you the details. Pushing the pH above 7, even though we are at equivalence. Okay, so let me just match up some of those terms here. We're at equivalence. We're at this nice stoichiometric point here. This is when to stop. It's actually the salt that's interfering. Well, how do we do hydrolysis? We take the salt, we break up the positive and the negative bit here. We cancel out the spectators. Well, sodium here is a group 1 salt. This one here is fully soluble. This is just going to be a spectator. Don't worry about it. But what about acetate? Acetate itself is actually a weak base. When acetate here is in the presence of water, acetate can actually steal a proton back from water and actually reform acetic acid. Now, at first you're thinking, oh, it reformed acid. Oh no, now it's acidic. But more importantly here, as it stole a proton from water, it actually generates some more hydroxide. Let's think in rough terms of amounts here. I have a huge amount of acetate. It's going to steal a little bit from water here. Only a small fraction is going to get over there because the Kb values we've been looking at are really tiny. You do generate some conjugate acid. Definitely that's going to be acidic. But we have so little of this, if we rely on this to end up giving it, oh yeah, this one here can also give back H+, that's going to be even tinier amount. Usually we just focus on, wait, by stealing from water, I ended up recreating some hydroxide. Even though we're at equivalence, even though the acid and the base have completely canceled out, we actually regenerate some hydroxide, and that's why the pH is actually slightly higher than 7. That would make phenolphthalein a really good indicator to actually change color. This time the phenolphthalein changes color between 8.2 and 10. Well, we are looking for an equivalence point, that halfway of this shooting up region here between somewhere 8.2 and 10. Okay, we're going to do all the calculations in tomorrow's lesson. I'm just going to end off with one other problem. I want you to just predict for me. What if I did the reverse? What if I did a weak base, strong acid curve? So let me give you an example of that. Let's take ammonia. Ammonia is a weak base. Let's react with HCl. I'll even predict it for you here. Well, it's going to be an acid-base neutralization. As a base, this is supposed to steal a proton. It's going to actually gain the proton from HCl. We're going to get NH4 plus, and we're going to get Cl minus, usually just written NH4Cl. Somewhere behind the scenes, it actually produces water. We know neutralization always creates water as well. I want you to comment for me. At the equivalence, at this special titration point, is the pH equal to 7, like the first case? Is it less than 7? Or is it bigger than 7? And explain why. All right? So let's just try it out again. At the equivalence point, moles of NH3 has just canceled out moles of HCl. At equivalence point here, we always have no reactants. That's always true. Okay? That would imply to you we should be neutral. That's what happened at a strong acid, strong base, and HCl couldn't hydrolyze. When I form this salt here, it would actually usually be written NH4Cl. I would have dissociated. Yeah, I get ammonium ions, I get Cl minus ions. Cl minus is a conjugate of a strong acid. This one here is a spectator. That one can't hydrolyze. The NH4 plus can hydrolyze though. So usually in a hydrolysis problem, we look for NH4 plus anywhere on our acid-base chart. We find NH4 plus down the table on the acid side. NH4 plus is a weak acid itself. It can actually regenerate some H plus and end up forming a little bit of ammonia. Because it is recreating some H plus, we would have the answer. Even though we're at equivalence point, even though we should be neutral, because we're replenishing a little bit more H plus, the pH is actually less than 7 at equivalence. So let me write that down in words. Because NH4 plus recreates some H plus, the pH is less than 7 at equivalence. And we can actually use a nice little memory aid here. For a strong acid, strong base curve, the pH is equal to 7 at equivalence. Earlier we did a weak acid, strong base curve. The pH was actually bigger than 7. I think of it as, was strong fighting weak, because the strong thing wins, it pushes it into its region. It's basic at equivalence. This last one here was a strong acid, weak base curve. This time the acid wins here. The pH is actually less than 7 at equivalence. That's just a memory aid. To actually explain this, you actually need to use which salt is actually hydrolyzing. Okay, so we'll review this a little bit more tomorrow with all the calculations and go from there. Thanks, guys.